Hello and welcome to my presentation where I'll be showing my investigation on the properties of unstable isotopes and their uses. Okay. So what are radioisotopes? Well, before we get into that, I think it's justified to do a quick summary on what an isotope is. Well, in basic terms, an isotope is just atoms of the same element with varying amounts of neutrons inside the nucleus. Like for example, carbon 14, 13, and 12. All of which have the same number of protons and electrons, but have different amounts of neutrons. A radioisotope is an isotope with too many neutrons in it and becomes unstable, causing it to decay into another stable state. Like for example, carbon 14. Carbon 14 is a radioisotope as it is unstable and it will decay into nitrogen 14. There are three forms of decay: alpha decay, beta minus and beta plus decay, and gamma decay. Let's talk a bit about half-life. Half-life is the amount of time it takes for a radioisotope to reach half of the original mass of the original radioisotope. Like for example, carbon 14 has a half-life of about 5,730 years before it decays to half of the original sample size before it's converted into nitrogen 14. Another example is iodine. Iodine 131, which has a half-life of 8 days, is converted to xenon 131. What is radiation? Well, radiation is the emission of energy from an unstable isotope during decay, which may come in the form of alpha, beta minus or positive, and or gamma. My phrasing of the term and or is because some isotopes like iodine 131 can produce both gamma and beta radiation. Radiation can be used for various purposes, which will be discussed a bit later. Alpha decay and radiation. Alpha decay is basically a radioisotope emitting 2 protons and 2 neutrons, or a helium nucleus. It is strongly ionizing as it has no electrons and is relatively a slow, big, and heavy particle. And because of these attributes, it has the weakest amount of penetration and it can be stopped by a few centimeters of air or a sheet of paper. Now, what can we use alpha decay or radiation for? Well, actually, a very interesting use for isotopes that undergo alpha decay is powering spacecraft. Alpha decay provides a steady source of power for some spacecraft like Voyager 1 and 2, maybe some new, also some like rovers on Mars, like a New Horizon, and I think the new one, Perseverance or something it's called, whatever. As it provides a consistent, steady flow of power that solar panels cannot reliably give, because the further away you get, the less sun you can absorb. I think it's called paraphylaxing or something. I'll put in the video. A common product that I hope we all use that contains a radioactive isotope that emits alpha particles are smoke detectors. Smoke detectors contain a bit of americanium, which is a radioactive isotope. Don't worry, it's completely harmless. Can't harm us because alpha particles are stopped by the air around us and by our skin, so they're harmless for us. Beta decay and radiation. Beta decay is the emission of an electron or a positron caused by a change in the nucleus. Beta radiation is moderately ionizing, it has more penetration than an alpha particle, but is stopped by a sheet of aluminium, and is also smaller than an alpha particle. Beta decay comes in 2 forms, positive and negative, which I will distinguish here. Beta plus decay is caused when isotopes have too many protons. During beta plus decay, a proton in the nucleus of an atom is converted into a neutron and creates something called a positron, which is ejected out of the atom. The mass of the atom is the same, but it loses a positive charge, so it decays an element down from the original element. Beta minus decay is caused when isotopes have too many neutrons. During beta minus decay, a neutron in the nucleus is converted into a proton and creates an electron that is ejected out of the atom. The atom retains the same mass similar to beta plus decay. The atom gains a positive charge which causes the element to decay up an element from the original element. Beta minus decay is beta minus. Beta minus decay is caused when an isotope has too many neutrons. During beta minus decay, a neutron in the nucleus is converted into a proton and creates an electron that is ejected out of the atom. The atom retains the same mass of the original atom, but it gains a positive charge, causing it to go up element from the original element. What are the uses for beta decay/radiation? Well, a well-known technique in archaeology and paleontology to measure the age of an object is carbon-14 dating. Carbon-14 dating is the measurement of the isotope carbon-14. Since carbon-12 and 13 are stable, they don't decay into anything else, but carbon-14 decays into nitrogen-14. Well, we measured the amount of carbon-14 in a sample because the half-life of carbon-14 is 5,730 years. Because of that, we can measure the amount of carbon in the sample because the carbon-14 makes about a bit less than 1% of the amount of carbon around us. So, with that in mind, let's say 5,700, like a 5,700-year-old fossil comes about. You can tell because, we have 1% around us, and the fossil has 50% left, because half of the sample decayed. Another interesting use of beta radiation is in iodine-131, which is used to treat thyroid cancer. The reason why iodine-131 is a perfect fit to fight against thyroid cancer and other diseases related to the thyroid is because the thyroid has specialized cells has developed, and they are the only cells in the entire body that can absorb iodine, which means that the gamma radiation emitted by the iodine-131 specifically targets the thyroid cells. This is very useful. It's because it's like having a precision missile. It directly goes to the thyroid cells. So if you have thyroid cancer and to get the thing removed, the iodine specifically target the thyroid, killing it, kills all the thyroid cells pretty much. Gamma decay and radiation. Gamma decay and radiation is unique compared to the other two forms of decay and radiation, as in that the emission contains no mass and isn't ionizing. Another thing that separates it from the other two forms is that the parent atom, or the original atom, isn't changed compositionally. In the other two, it changes the composition of the atom. It removes a proton, changes an electron, blah blah blah. But in this one, it just removes energy. The atom stays the same, it just loses a bit of energy. Gamma radiation is the most dangerous form of radiation for us and biological life in general, as it can penetrate most materials with ease. It can go through me, go through my house, my neighbor's house, and kill the dog or something. So what does it take to stop a gamma ray photon? Well, it takes a few centimeters of lead to stop it, to absorb the thing. And lead is quite expensive and toxic to us, so you can't touch it really without equipment, So how can we use gamma decay/radiation? Well, gamma radiation is widely used in the field of medicine, serving as an effective way to sterilize medical equipment, as gamma radiation is very harmful to DNA and most little things in DNA. Actually, interesting story about sterilization. During, I forgot the exact time, it was late 80s, late 90s, yeah, where there was a Dutch lady that got infected by a brain prion. Prion's a little bit of protein that it's like a virus. They're not alive, but they still infect you. Well, a prion survived on a piece of sterile metal for over 2 years and infected the woman. Gamma rays are also used to sterilize food, as it can kill many harmful cells or microbes in the food we eat. Gamma rays are also used in oncology, which is the field about cancer, and radiology as an effective method in killing cancer cells and tumors, because it disrupts their DNA. Now, time for everyone's favorite part of the presentation, the bibliography. Yeah, woo, let's go, bibliography, yeah.